having it will be connected to some CPU chip. The CPU chip will be dissipating heat to it, and we need to dissipate that heat. So we will add fins on the surface like that, and we will supply the air from the fan to increase the heat transfer to the fluid. All right. Okay, so these are the fins in that case. So electronics cooling. You can also see on the electric motors of the two-wheelers. Okay, the fins are there. Okay, in that case they will be called as air-cooled EV motors. Okay, so there are different fin configuration we can have. So fin configuration, if we'll see, there are different fin configurations we should know, and these are straight fin of uniform cross section. If if to the plane wall we attach a straight fin can be of uniform cross section and also of non-uniform cross section, like this. This is having width W, thickness D, and its cross-sectional area we can find like W times D. Okay, so this is straight fin. Okay, this is base surface on which we are attaching the fin. All right, and next, straight fin of uniform cross section. Then on the base surface we can attach the fin of non-uniform cross section. All right, like this. Its cross section will vary with location, but it is straight, right? So at any location it will have different cross sectional area. This is also straight fin, but fin of non-uniform cross section. Okay, all right, and the fins which are wrapped around the cylinder are called radial fins. All right, like you can see around the cylinder block and cylinder head of motorcycle engines. So they are circumferentially surrounded to a cylinder like this, and there are multiple fins because in that cases single film will not be sufficient to dissipate the heat dissipate the required amount of heat, like this. Excuse me for that drawing. I'm not good at the drawings. And they are called annular fins. And here the important direction is radial direction, and the last important configuration of importance to know about the fin heat transfer is pin fin. Pin fin or spine fin, because they are having circular cross section. All right. They can also be of uniform and non-uniform cross section. Okay. So in any application, which fin we have to use depend on the space available, the weight, manufacturing and cost consideration. So deciding which type of fin we should use is dependent on various parameters, like all right, because when fins are attached to the extended surfaces, and they also incur the pressure drop, and pressure drop is directly related to the pumping power of the fluid flow through the fins. All right. If we think about the radiator, in radiator we will having the fan which will blow the air when the vehicle is stationary. So required flow rate amount of air will increase, which means pressure drop will increase if we do not put the correct configuration of the fins, and also if we put fins in a wrong way. All right, it is directly related to the pumping power, so we should trade off between those things. All right, so but we are engineers. We are primarily interested in knowing the extent to which a particular extended surfaces of fin arrangement could improve the heat transfer from the surface to the surrounding fluid. And to determine the heat transfer, we must know the temperature profile in the fin. All right. So to determine the temperature profile or temperature variation inside the fin, we will follow an energy balance approach that we have used till now in all the applications, right? So a Chernal thermal conduction analysis, we can name this fin conduction analysis also. Let's say fin conduction analysis. All right. So before doing this analysis, we'll assume things so that the analysis can be simplified. All right. First of all, let's draw a simple diagram to illustrate what we mean by this analysis. To perform this analysis. Let's say this is the base surface. And this is the fin attached to it. and this is the x direction, this is y, this is z direction. And consider differential volume of this fin. So in this fin, what are the things that is happening? So it is receiving heat from the base surface, and it is dissipating to the environment. That's it. So at any point inside this fin, so this point, this point, this point, this point. So at any point inside this fin, the rate at which the heat is transferred to the fluid, let's say this is T infinity and H, the rate at which it is transferring to the fluid by convection at any point is balanced by the net heat conduction from all directions to this point. Net means whatever is coming in minus going out, right? But in practical cases, fin is generally thin and temperature variations in the y and z directions can be neglected. So to simplify our analysis, we will assume that at any point, at any location inside the fin, the temperature will be only a function of x. Alright, so we can reformulate the statement that rate of heat transfer, so at any control volume inside the fin, what is happening? The rate of heat transfer to the fluid is because of the net conduction heat transfer to that point. Since we are assuming one-dimensional, so we will write assumptions here. One-dimensional heat transfer. Okay, why? Because fins are generally thin in practice. Also, we will assume steady state case. Okay, and no internal heat generation inside the fin. And constant thermal conductivity. That is, there is no